Here is a sequence you might have seen before. Begin with two numbers, and usually these numbers are chosen to be 0 and 1. To get the next number, you add together the previous two. Same goes for the next one, and if you keep going, what you will find is a rapidly growing sequence. This is called a Fibonacci sequence, and the question is, without calculating all the previous sequence members, can you tell me what the value of the 30th Fibonacci number is? As it turns out, there is a formula to calculate every one of them, and within it you will find two special numbers, often called the golden ratios. They are the kind of numbers that come up all over in math, and as you will see, there is a very good reason why they are here, because in the next minutes we are going to derive it using nothing but the basics of linear algebra. That said, in order to understand what follows, you need to know about matrix multiplication, and it is helpful to have heard about eigenvectors and eigenvalues, although that is not required since I'm going over the topic anyways. With that in mind, the key step here is to figure out how to transform this problem that uses sequence members and its rule into a problem that uses vectors and matrices instead. If you want, you can pause here and come up with an idea, otherwise I will just go ahead and reveal the answer. The idea here is to use the Fibonacci numbers as the entries of your vectors, and since you always need two consecutive numbers to reach the next, it could be a good idea to pack these two members into one vector. Now, how do you get from one vector to the next? This is again a good spot to pause. It's not too hard, and as a hint, it's by multiplying with a certain 2x2 matrix. Alright, the matrix we're looking for has a 0 and a 1 on the diagonal and 1s on the off diagonal. When multiplying our vectors with it, the bottom entry becomes the top entry, and the new bottom entry is the sum of both entries, which by definition is our next sequence member. We can keep multiplying our vector with this matrix, and each time we do, the entries become higher and higher Fibonacci numbers. Looking at this, we can see that we can solve our problem by multiplying the matrix n times with itself, then multiplying it with our start vector, which remember has 0 and 1 as its entries, and then look at the top entry. So the real task here is how to calculate this matrix. If you were to just brute force it, you will see we didn't really make the problem easier, so we need a different approach. If you're already more familiar with linear algebra, you can do that using diagonalization, however I will show it using another way. In order to go on from here, it helps to get more familiar with the transformation itself. Here you can see how the transformation acts on a whole range of values, together with the canonical unit vectors. It can get quite messy if we try to apply the transformation multiple times. However, this is not why I show you this. For now, I want you to focus on two different vectors and see if you notice something after applying the transformation. Unlike the canonical basis vectors, which get shifted around, these two vectors stay true to their line, only getting stretched or squished. And mathematically, stretching or squishing just corresponds to multiplication by a number. These special vectors are called eigenvectors, and the value they get multiplied by is their corresponding eigenvalue. There is a common technique on how to find these vectors, but getting into it would be too much for this video, so for now I will just tell you. Now you will encounter the two special numbers from the beginning again. The first vector has coordinates 1 psi, and its eigenvalue is psi, meaning after the transformation it gets squished by its value. The second vector is 1 phi, and its eigenvalue is phi. After every transformation, they get again multiplied by their eigenvalue. Going back to matrix notation, what we just discovered is multiplying our eigenvectors with the matrix results in multiplication by phi. Since multiples of eigenvectors stay eigenvectors, we can multiply with the matrix again and again. Let's take a step back and see what that actually means. It means that if our two starting numbers of the Fibonacci sequence weren't 0 and 1, but 1 and phi, we would get an easy solution to our problem. By definition, the next sequence member is the sum of the first two, giving us 1 plus phi. But since we established it's an eigenvector, this is the same as phi squared. By the same logic, we can easily calculate all following sequence members. The same goes of course for the second eigenvector as well. Unfortunately, our starting numbers are 0 and 1, so how do we deal with that? Well, there is a way, but for that let's take a look at the grid again. The yellow vector is our starting vector, whose transformation we want to track, and the red and green vectors are our eigenvectors. The idea here is to write the yellow vector as a composition of our eigenvectors. This way we can track the transformation quite easily, and we just need to keep in mind that we care about the sum. This looks pretty in theory, but how do we do that mathematically? Well, just as described, we want to rewrite our starting vector as our first eigenvector times some number plus our second eigenvector times another number. We can find those numbers by writing out the vector coordinates, giving us a linear system of equations. This we can solve using a bit of algebra, which is not that hard. That's why I did it for you. Now we are almost there. All that is left is using all we have learned in the last step. For that, I will write out the matrix equation from the beginning. We can substitute our eigenvector expression for our starting vector and distribute. We know what this gives us since it's an eigenvector. The same goes for the other eigenvector. Putting all together, we finally get our answer. As mentioned, the first component of the resulting vector is our nth sequence member, which is exactly our formula from the beginning. I could end the video right here, but I would like to make a slight improvement to the formula. So far, we have only solved it for one specific starting condition. But what if the starting numbers are arbitrary? We don't have to work very hard for our answer. If we expand our starting vector into its canonical components, we can already recognize part of it. To solve it once and for all, we can use the fact that the second canonical basis vector is just our first canonical basis vector after one transformation. Taking the inverse on both sides gives us an important expression. Now we only need to substitute this and simplify. This part we have already calculated, and this part is really the same, only it's n-1 instead of n. We can put all together in one vector, and again we only have to look at the top component to get our formula. So there you have it, a general expression for a Fibonacci sequence with arbitrary starting numbers. The fun thing about math is you can always make things more difficult. For example, what happens if we change our rule for the sequence members to take the second term times 2? Or what happens if you take the sum of the last 3 members? Both of these questions can be solved using a similar approach with matrices, but I'm not going to spoil it here. So for now, I'm done.